Well, thank you very much for having me. I'm glad to be able to speak to all of you again. So I'm Preston Smith from Purdue University. I'm going to talk about how our AI computing investment is part of the foundation for our institutional strategy at Purdue. So Purdue right now has four major pillars, strategic projects. You can see here, well, a new campus in Indianapolis. If you're familiar with Indiana geography, Purdue is between Indianapolis and Chicago, about halfway. And Indianapolis will be at the other end of a hard tech corridor connecting West Lafayette with Indianapolis, building out pharmaceutical workforce, advanced manufacturing, all the things that AI is enabling. We have an initiative, which I talked about last year, Purdue Computes, which brings together physical AI, Purdue's leadership in semiconductors and quantum computing, One Health, applying AI to the intersection of plant, animal, and human health, and then reimagining our Daniels School of Business with a STEM-based business school. So at the bottom of this, of all these pillars, is AI computing capabilities, is central to making sure all of these things happen. Just as an aside, I really liked the language earlier when Alex and Paul mentioned sovereign AI. I think I'm going to have to start using this in higher ed because in a lot of ways it's the same sort of thing. It's important for universities to have sovereign HPC and AI capabilities to make sure that we're able to be competitive. Some colleagues and I did some research here, if you're interested in reading some economics, about what that actually translates to in higher ed. By investing in our AI and compute capabilities, it translates directly into the outcomes of the university. For every 100 teraflops of capacity that we provide, it leads to an additional $3 million of research expenditures coming through the university. It allows us to graduate more PhDs. And similarly, by staffing up your research computing organization, you get substantial returns as well. The center of our AI strategy is our community cluster program, which I won't go into a lot of details about that. But we support on campus nearly 300 faculty members. They all invest their grant dollars into a central resource that they can all share. In a lot of ways, we're like a cloud for the university in that sense. But we delivered over 1 billion CPU hours last year. Computation is affecting every domain at Purdue. And then also our Anvil machine there on the right is one that we operate for the National Science Foundation and the Access and NAIR program as well. DDN underpins all of these machines. I couldn't remember the model number, but we got our first DDN service in like 2004 or so, running iBricks on that hardware. If any of you guys remember some of that technology. But we've got these machines in production today, all of which are running exascaler. Anvil is running GPFS on DDN hardware. And it serves everything from open science with modeling and simulation workloads, with AI-heavy workloads, and even our NIH enclave for projected data, taking advantage of the encryption features that are in Exascaler. A couple of highlights for what these resources enable. This is one that's in that semiconductor pillar. We have researchers doing material simulations where they're looking at the atomic level inside their semiconductor design. And they'll use AI in this situation to lower their time into science so they don't have to do expensive physics-based simulations. Just let AI get these things and get results faster. On the national side, Anvil supports a lot of great research. This is one that was just their highlight published recently with a researcher at Arizona State who is using AI to deploy a foundation model for diagnosing health based on medical imaging. One of the things that I was asked to mention was this is a cool effort that's happening out on the show floor. So when you get into the exhibits hall and when you go by the SciNet NOC, you'll see you'll see these racks not in a warehouse, but on prime display there in the SciNet Network Operations Center. When you think about SciNet, it's a really, really fast network, right? It has, I think that I heard them say that there's something like 16 terabits of network going across the show floor. But a lot of us, our interaction with it is our Wi-Fi. But the vision is like, we have this great network, it's about building things for science. How can we make the SciNet network actually support science while we have it up and running? So this is the second year where we've got a cluster running on the SciNet floor. Everything about it is faster. It's got faster networks. It has faster storage. Thanks to working with DDN on that, it's got 100 gigabytes a second of connectivity to an exascaler file system. It's already integrated with the National Research Platform, so workloads will be coming into the supercomputing floor from all over the world, advancing research in high-energy physics, networking research itself, and various other projects that might be coming in from the open science pool. And then finally, the last thing I'm going to talk about is our new Gauchi system and our benchmarking efforts on that. So we deployed this machine, just turned it on and got a top 500 run last supercomputing. So it entered production earlier this year, and it's been running real science workloads ever since. But one of the things that this machine allowed us to do is such a great AI resource, and it has far and away the most IO capabilities that we've ever operated. It's based on the 400 NVX2, 3 heads, about 9 petabytes of capacity, and it's the fastest thing we've ever run, which you'll see a slide here in a second. Exascaler is very important to us. We're eager to figure out how our researchers can start adapting object storage at some point in the future. But POSIX, like it or not, is very much alive in higher education. Those old codes, they have their ways of operating. But last year we were able to run an IO 500 run on Gauchi untuned. It was really good when it came out of the box. This is just a basic untuned 10 node run, and we compared this to all of our other existing systems. You can see how much faster it is just out of the box without doing any hard work. We were 3x the bandwidth and 5x the IOPS of our previous new system, which is a SAS-based exascaler deployment. But that's great. It shook down the system. We know it works, but we know we have a really nice file system here. So one of our goals for this year is to actually get the thing benchmarked and get it onto the IO 500. Hopefully we'll. I saw the graphic earlier with how many DDN systems there on the IO 500. Hopefully we'll add one more when the BOF happens later this week. But we worked closely with the engineers at DDN. We leveraged some of the recipes they had gotten from getting other machines up and going. I'm excited to hear Eric Duman's talk later about their benchmarking in Florida. But we were able to tune the benchmark and got a lot better results. So we increased some of those numbers, had a factor of 146% to over 2,000% faster just by doing a little bit of tuning and relying on those recipes from DDN. So it got a score of 70. I don't know how that's going to hold up in this next list, but the BOF, I believe, is on Thursday. So we're eager to hear how that plans out.